this is the metal part, this is silicon dioxide oxide part, and this is the semiconductor part. This is the MOSFET. And this terminal, the MOSFET is a 3-terminal device. So this one is gate terminal, the metal part. And you have two AND well. If you have two AND well, this terminal is the source terminal, and this terminal is the drain terminal. And that can be done at P-type substrate. Another one can be just opposite, P plus, then N substrate, then you have oxide layer, then you have metal layer. The gate terminal is the same. This will be the source terminal, this is the drain terminal. In case of B MOSFET, depletion type MOSFET, the channel, the source and drain will be connected. That means there is a channel from the very beginning. We just apply to some voltages here, then we'll get, sorry, not here, we'll get some current here. But in case of E MOSFET, there is no channel at the beginning. That means we have to apply some gate voltage. According to that, a channel will be formed and the source and drain will be connected. Here, in this case, we will use our E MOSFET. That means by controlling the gate voltage, we will just create the channel. Because when there is a channel, there will be current flow. When there is no channel, there will be no current. As we are trying to get the logical circuit, logic gate, either 0 or 1, that's why we need to use this kind of MOSFET, E MOSFET. So that we can, by applying the gate voltage, we can control. By controlling the gate voltage, we can have some current, we don't have current. So this is the D MOSFET and E MOSFET. And so this is the MOSFET, metal oxide semiconductor. So the conductor, it can be P-type substrate. So here, as you can see, is a PMOS, this is a P-channel MOSFET. That means here it is an N channel because we have N-type source and N-type drain. So we have a connecting a channel. This is an N channel because we have an electrons here. So sometimes some of the students get confused with the P-type substrate with the N channel. So to get this N channel, we have to have a P-type substrate. These semiconductor will be P-type. Then we create an N1 to N1 for the source and the drain. Then by applying the gate voltage, we create this channel. Then channel is created. That's why it is known as N channel E MOSFET. In short, it is called NMOS. Oppositely, if you want to create the P channel, you have to take the N-type substrate, then take the TOL, then you have to apply gate voltage. So in case of N channel, we already, if you have just from recap, if you have this N channel, to create this N channel, so you have P-type substrate, we have N here, we have N here. So to get this electron here, we can think like this is a parallel plate capacitor. So this is a metal plate and this is a semiconductor plate. So you want what? The negative charges here. So if you want to get a negative charges here, that means you want to get a positive charges here. That's why you have to apply a positive gate voltage. If you apply a positive gate voltage, then you will get the negative charges here. So that's when we can create an N channel here. So if you want to get a PMOS, then you have to apply negative gate voltage. Okay? This is just for the idea. Okay. So here we will discuss our complementary metal oxide semiconductor to design the logic gates. So the CMOS based logic gates uses the complementary pair of the PMOS and NMOS. That means in case of CMOS, we will use both the PMOS and NMOS. It is possible to design any logic gate by using NMOS itself. We can design a NAND gate, we can design NOR gate by using the NMOS or also the PMOS. We will see. But there are some drawbacks or some problems. That's why we use the CMOS. So CMOS based logic gates uses a complementary pair of PMOS and NMOS. So if I draw the symbol of PMOS and NMOS, so this is gate. If it is, I call this is an NMOS, then this is the drain source. Yeah, this is the source and this is the drain. So if you apply VDD here and the source is connected to the ground, when you apply the sufficient gate voltage, when the gate voltage will be more than our threshold voltage, a channel will be formed. That means if I draw again this diagram, it will be easy to understand maybe. So this is my metal, this is my oxide, this is N plus, N plus. So this is called PGS, potential difference between gate and source. Gate and source. This is source, this is gate, this is drain, and this is called VDS. When you have sufficient positive gate voltage here, the channel will be formed. When the channel will form, now we have this potential here, VDS. Now the current will flow from drain to source. Electrons will flow from source to drain. This is known as source, and the electrons are going to the drain. It's known as drain. Electron is coming from, current is flowing from drain to source. So current is flowing from drain to source. So arrow is upward direction. This is NMOS. In case of PMOS, it is just opposite. Now this will be my source and this will be my drain. The source will be connected to the VDD, positive, and the Y. If you want to get a PMOS, what we have to have? A negative gate voltage, right? VGS. So that means your source should be at higher potential. Negative gate voltage means it's not always have to be -1, -2. That means this is a potential difference. Here VGS, we write down this VGS, it means VG minus VS, a potential difference between these two nodes. So that means you get at higher potential. In case of PMOS, it's supposed to be VSG. That means it will be VS minus VG. Your source will be at higher potential. Now the source is connected to VDD. You can connect like this. Okay. So now current will flow from this direction. So you can use this symbol. So these are the two symbols. Again, I'm drawing. So by this one gate, this one source, this one drain, VDD or VCC, whatever you say. This is the ground. Here we have another. This is one. This is source. This is drain to the ground. This is gate with the arrow. Sometimes it is not so easy to memorize or remember. So what we can do, we can just think that this is NMOS, this is PMOS. In that case, we will not use any arrow. We just can use a bubble. Here we just can use a bubble. Here we don't have any bubble. Here we have a bubble. It can also, in some books you can find out this is the symbol of NMOS and PMOS. In complementary CMOS, we will use the pair of both NMOS and PMOS. So as I mentioned, so if it is an NMOS, if you apply this gate voltage VG, because you can see here, this is VGS, right? We are applying VGS, right? Look at here, VGS. So that means this one is the VGS. If this one is VGS, my source is connected to the ground. So VGS, as I mentioned, what? VG minus VS. So VS equals to ground. So we can understand VGS equals to VG. Can I say easily? So that means you have to have some certain voltage which one should be greater than equals to threshold voltage. In case of NMOS, we can write down VTN. So this is threshold voltage for NMOS. So your gate voltage should be greater than of threshold voltage, then a channel will be formed. That means this MOS will turn on. You can say it will be on when VGS is greater than VTN. Am I going fast? Okay. Good. So, if VG is less than VTN, it will be just off. So we can say that here the MOSFET is acting like a switch only. We already discussed in our electronic circuit, right? We can use MOSFET either as an amplifier or as a switch. If you want to use a MOSFET as an amplifier, you have to have in the active mode, active region. In that saturation region, let's have the VGP in the active region, but the MOSFET in the saturation region, so that it can act like a constant current source. But if you want to use your MOSFET as a switch, either it will be in cutoff region or in the saturation. So here this one is that. So if VT is less than VTH, it will be off. No connection between drain and source. There is no current then from drain to source. If VT is greater than VT or the threshold voltage, the MOSFET will turn on. There is a current from drain to source. So what about the PMOS? The PMOS will be just opposite, right? PMOS will be just opposite. In case of PMOS, it will be VSG. In case of PMOS, it will be VSG. So here VSG, if VSG is less than VTP, threshold voltage of PMOS, that's why it's TP, then it will be turned off. If VTP is less than, VSG is greater than VTP, it will be on. So they will be just complement each other, right? Complement to each other. PMOS and MOS is complement to each other. So whenever we use this CMOS, it's a complement to CMOS because we are using PMOS and NMOS together. Okay. Now we have NMOS and we have a PMOS. Whenever we have our CMOS circuit, we'll call it a pull-up resistor and a pull-down resistor. A pull-up resistor and a pull-down resistor. So here we have connection to VDD or VCC, whatever you say. Then we will have a pull-up resistor network. So this pull-up network is designed by using the PMOS. And then we will give it to another circuit, which is known as pull-down network, and this pull-down network is designed by NMOS, and then it is connected to the ground. We give our input here. We can think like giving input like this, or we can individually think like we have input here, we have input here, and we take our output from the circuit. Is a ground. So PMOS are used in a pull-up network because PMOS transistors can easily pass logic high. It cannot pass logic low. A PMOS transistor can easily pass I will show you logic high. It cannot pass logic low. On the other hand, NMOS transistor can easily pass logic as they can easily pass logic high, the PMOS, that's why they are connected to the VDD, close to the VDD. As NMOS can easily pass logic low, that's why they are connected to close to the ground. We'll see why it is mentioned, but this is the, at that moment, if you want to design a CMOS logic circuit, we have to have a PMOS and NMOS. The PMOS transistor will be connected to close to the VDD. We call it pull-up network. So that whatever the logic input is, they will close to the VDD, logic 1, logic high, and this NMOS should be connected to the logic 2. Okay. So if I want to design a very simple CMOS circuit, so here we have a PMOS, here we have an NMOS. If you draw the circuit here, so PMOS, so it is source connected to the VDD, this is drain, and then it is NMOS, source connected to the ground, this is drain, this is my output, and this is my input. So if you just don't have to use arrow, you can pull like this, no need to put an arrow, just put a bubble here. So here, no bubble, NMOS, with bubble, PMOS. If you don't bubble here, you just see that current is flowing from source to drain. On the NMOS, current flow from drain to source. So arrow will make sure that current is flowing from drain to source here. Arrow making sure that source is connected. So these are the gate terminal. This is source terminal, this is drain terminal, source. So this is the circuit or symbol of a CMOS. Before going to the CMOS circuit, let's try to design an logic gate with NMOS circuit. NMOS inverter, the very basic one. NMOS inverter. If I design an NMOS inverter, that means we have an NMOS here. So this is the source, this is the drain. Then we connect a resistor RD, drain resistors. This is VDD, this is my gate terminal. We take our output from here. Right? So when VGS, so here we apply the gate voltage as I mentioned, a positive gate voltage, VGS or VG, is greater than your threshold voltage, what will happen? Your MOSFET will turn on. When the MOSFET will turn on, it will connect it to the ground. That means you will take your output from this node with respect to the ground. As it is connected to the ground, it will give you zero. That means you are giving high, logic high, you are getting 1, 0. So that's why it is an inverter circuit. Now when you are giving logic low, that means your gate voltage is less than your threshold voltage. This transistor will remain off because there's no channel will be formed here. If the channel is not formed here, it is off. That means it can like an open circuit, right? So we can think that this is open. So you get your output according to the VDD. Some voltage up here, you get 5 volt, whatever you apply, 5 volt, 3 volt, you get. You apply 5 volt, 1 kilo ohm here, you get. So it's a logic high. You are giving logic low, you are getting logic high. So this is an NMOS inverter circuit. That's very simple one. Okay. So now as I mentioned, Y and MOS can easily pass logic 0 but cannot pass logic high. Okay. So think like this. This is my drain to source voltage. This is drain, this is source, and this is my gate. And we apply logic 1 here. That is high, VDD. So gate is, when you apply the gate voltage, logic high, your transistor turn on, right? You give your input to the drain terminal. You are expecting output at your source terminal. You just give the logic high here, the gate is on, so transistor is on, because it is more than threshold voltage, channel is on, you just apply the signal here in the drain terminal, you then have the output at the source terminal. So now when this source terminal, if you think like there is a capacitor connecting here, a capacitor here, when the current will flow, the capacitor will keep charging, right? Capacitor will keep charging. So when the capacitor will keep charging, at some point, this Vs, the source, at the source terminal, the gate voltage will keep increasing, right? And it will reach at some point, it will reach Vs is equals to VDD minus VTN. Like a pinch of, that's why the pinch of happened, right? The source voltage, the current is flowing here, the capacitor is charging, right? At some moment, this source voltage will be equal to this VDD minus VTN. VDD minus VTN is made to turn on voltage, right? To not turn on this device. So Vs, then we will calculate VGS. At that time, if we calculate the VGS, what is VGS? VGS is equals to VG minus Vs. What is VG here? VG here is VDD. And now Vs what? VDD minus plus VTH. VDD and VDT will cancel it. That means it cannot, so we can write down that VGS is equals to VTH. That means, it means that after some threshold voltage, it cannot go beyond that voltage. That's why the NMOS is not good for passing logic high. There's some threshold voltage. It can reach until the threshold voltage. It cannot go beyond that. But to apply the logic high, we have to have more than 3 volt, around 5 volt, right? Otherwise, it will not be a logic high. It will be in the intermediate region or in the logic 0 region. So we can see here, if we use logic high, that means it cannot charge until the logic high level, some threshold voltage. So that's why it is saying that NMOS is not good for passing logic high. So NMOS is good for passing logic 0. That's why NMOS will be connected, or we can design the pull down network by using NMOS. That means it will pull down to the ground, logic 0. Okay?
Due to this capacitance, it's created.
Capacitance is just giving us an idea how the capacitance charging. When you are we don't have to put another capacitance here, just for charging. Then during the when off state, then it will discharge. Now we'll see during the resistor for the PMOS, why PMOS is good for passing high. Then we'll see how this capacitor helps us to understand.
These are like parasitic capacitance, right? Due to the transistor inside
there is capacitor. We didn't consider those capacitors. The parasitic capacitance, the inside, we have oxide capacitance,
yeah.
We have the overlapping capacitance. We didn't consider these things. Okay.
Those are the reason this capacitance is happening, or
no.
Okay.
Those capacitance is related to the speed
Okay.
of our device. The speed of our device. You have to calculate those capacitance value. You have to know the capacitance value so that you can determine the speed. And if you want to improve your speed, then you have to play with the dimension during the fabrication. How narrow you can decide this oxide layer or the overlapping layer. Okay, so if you reduce the area, then you can reduce the capacitance values. But you cannot remove the capacitance value. There will be always capacitance. The most maximum capacitance of the device is the outside capacitance. That was the maximum one. Okay. So here we have this p-type, n-type, then this oxide, TOX, thickness of this oxide there. So this is the oxide capacitance, is known as TOX by epsilon naught OX. The permittivity level of this oxide. So usually we use the silicon dioxide, permittivity level is 6, and the thickness of this oxide. So if you want to reduce the oxide capacitance, then you have to reduce the thickness. But you cannot remove the gap, right? So there will be minimum. But this capacitance is the maximum capacitance of the device. There will be an overlapping capacitance, but they are not overlap this capacitance now. This is the highest capacitance, oxide capacitance. Okay. So we can say that to keep this NMOS on, the VGS should be always greater than VTN. If they become equal, it will off. If they become equal, it will off. So if output goes beyond this VDD minus VDD, then it will turn off the NMOS. So NMOS is not good passing logic 1. If it is stopped, then we cannot pass anything, right? So that's why it is mentioned that NMOS is not good passing logic high. So NMOS is good for passing 0. So what about the PMOS here? In case of PMOS, so now if you just put a bubble here, and if you connect a capacitor again here, what will happen? Now we'll give logic 0, right? To turn on. The opposite one, to turn on, we'll give the logic 0, close to the ground or something. So when output reaches to the threshold voltage, so that means VSG is equal to Vs minus Vg. So what is the Vs? Vs is reached to the threshold voltage, and gate voltage is 0. So VSG will become VTP. But to turn on, this VSG should be greater than VTP. But they become equal. Because my VSG means Vs minus Vg. And now at the source terminal, you reach to this threshold voltage, and the ground gate voltage is 0 because you apply the logic 0. Right? Logic 0. So when they become equal, this transistor will turn off. That's why PMOS is not good for passing 0. PMOS is good for passing.
Can you explain one more time?
Okay, we are talking about now PMOS.
PMOS.
So if you want to PMOS, that means you have to apply negative gate voltage or 0 gate voltage to turn on. The opposite of the NMOS. So you apply logic 0. Then it's turn on, fine. Grind is going. The source voltage, here the voltage is reaching some threshold voltage. So when this Vs reaches to that threshold voltage, that means threshold voltage is what? VTP. So Vs equals to threshold voltage, and gate voltage is 0 because you apply logic 0. If you see that, now VSG is equals to threshold voltage. But to keep turn on this MOSFET, this VSG should be greater than.
VSG should be greater than, yes.
The MOSFET will turn off. So we can say this PMOS is not good for passing logic 0. That means PMOS is good for passing logic high. So I'm writing here, PMOS is good for passing logic high. NMOS is good for passing logic. Did I make a mistake? So that's why PMOS, by using the PMOS, we will design pull-up network. By using the NMOS, we will design pull-down network. This pull-down network will be near to the ground. This pull-up network will be near to the VCC or VDD, whatever you say. Okay? Okay. what is the problem with this NMOS if you use the NMOS or PMOS only? If you use the NMOS and PMOS only, the problem is the static power dissipation. Static power dissipation. That means whenever we are using the NMOS, for example, we are using this NMOS. So whenever we apply logic high, this transistor, the MOS will turn on. When the MOS will turn on, and VDD to the ground, they will get a path. So a huge current will flow from here. So power dissipation will be increased. And here in the IC, it is not only one transistor, hundreds or thousands of transistors. So power dissipation will be very high. They will get a short path from VDD to the ground. You can see a very short path from VDD to the ground. Instead of using this NMOS or PMOS, if you use a CMOS, they will not get the direct path from VDD to the ground. So it will reduce their static power dissipation. So that's why we use a CMOS instead of NMOS and PMOS. Another thing, so this one. So next thing is, in case of IC design, we're talking about the IC, right? Integrated circuit design. It is not easy to design a resistor because it will take a lot of space. So we already know, whenever in my 433 in analog electronics, we can replace this RD by an active load. One of the active load is a diode connected load, right? The diode connected load means if you just connect the drain and the gate, it is known as a diode connected load. So we can use a diode connected load instead of a resistor. We can just replace this resistor. If I draw this one, it will be this was my previous NMOS. This is the gate, this is the source, this is the drain. Previously we have a resistor here, right? Instead of resistor, we are putting our active load. This is known as diode connected load. A diode connected load means the drain and the gate are shorted. So both are now NMOS. It is not a CMOS. That's why don't get confused. I'm drawing an NMOS and PMOS. Both are NMOS here. We are just replacing our resistor with a diode connected load. This configuration is known as diode connected load because a diode has two-terminal device. MOSFET has a three-terminal device. Now, whenever we shorted this gate and drain, it also becomes two-terminal device. That's why it's known as diode connected load. So, if you connect a diode connected load, what will happen? So that means you are connecting your gate to the drain, short and connected to the VDD. That means this transistor will be always on. Will be always on. So if when it is always on, we can replace this diode with a resistor, right? And load resistors are. This is not an actual resistors, but they have some resistors just for the channel length modulations. So there is a resistance here from drain to source. And this value you can control the value. You need some kilo ohm resistance. For example, we can make that sure, making sure by W over L ratio of the diode. W over L ratio of the diode, because W over L ratio is the channel, right? So this is the important thing. This is the channel. So if you draw the MOSFET curve, this is the characteristics. In this region, triad region, your MOSFET act like a variable resistor. It's a resistor, the slope. So this is the resistance from where? This is from the channel. Because you are getting this current whenever there is a channel. So by controlling the W over L ratio of this channel, we can just determine our required resistance. So you don't need to have a resistor. Instead of a resistor, you're just using a transistor, a MOS. We can make sure this is a resistor. It's known as active load. So by changing the MOSFET device parameters like W/L ratio, it is possible to ensure that its on resistance is neutral on resistance. So here the resistance is known as on resistance, right? Can you remember from 433? This is known as on resistance, and for this on resistance we have some equation how to calculate this on resistance. Okay. So you already talk about this NMOS passing logic 0, PMOS passing logic high. Okay, good. Now, so we have pull up resistor, we have pull down resistor.
Professor?
So I go to the NMOS, the CMOS now. So my CMOS. VDD, this is ground. We take our output from here, and give our input here. So this is a PMOS in a pull-up network, pull-up network. This is NMOS, pull-down network. Right? This is both our gate terminal. This is the source terminal, this is drain terminal, this is drain terminal, this is source terminal. Okay? This CMOS usually at the normal CMOS is an inverter circuit. It's an inverter circuit. For example, when we put the in is equals to 0, this is my input, right? And this is my output. When you give the in equals to 0, logic low, whatever you say, what about this NMOS? NMOS will turn on or turn off? Off. Everyone agree? Whenever we give logic 0 or 0 voltage, this will be off. And this one is a PMOS, it will be on. So if it is off means this transistor will act like an open circuit. So we can just disconnect this one. Whenever we get output equals to VDD. We are giving logic 0, we are getting logic high. Now, if you give V input at high, 5 volt, 3 volt, or just say logic high, now this transistor will be turned on, and this one will turn off. If it is turned off, that means it will be disconnected from the circuit here. We will get our output with respect to the ground. It will be logic. So we can say that a CMOS is actually an inverter circuit. A CMOS is an inverter circuit. And as I mentioned, the static power dissipation here will not get a direct path from VDD to ground. In case of NMOS, just only an NMOS, just only an PMOS, when the transistor will turn on, there is a short path from VDD to the ground. Right? If I just draw the NMOS, this one. If it is turned on, we'll get a short path here. But here, one of the transistor will always remain off. So there will be no connection between source and the ground. So it is an advantage for this CMOS over NMOS and PMOS. Okay. So since PMOS passes strong logic 1, as I mentioned, the output will be very close to the supply voltage. Okay. Since PMOS are very good to pass logic high, so output will be very close to the VDD when PMOS will be turned on. Since NMOS is very good pass to logic low, So it will be, when it will be turned on, it will be very close to ground. So from, we know in the CMOS, we can consider logic 0 from 0.2 volt to 0.8 volt. And for the logic 1, we consider from 3 to 5 volt. Okay. So both the transistors are not on at the same time, so there is no direct path from the VCC to ground, and due to this, the static power consumption of CMOS is almost negligible. It's almost negligible. Now let's try to design the AND gates by using the CMOS. At first, let's try to design the AND gate and NOT gate. Before going to that, we have one more concept to be very clear. The first concept is this one, right? Pull-up network, pull-down network. Pull-up network will be consist with PMOS. Pull-down network will be consist with NMOS. In digital logic design or logic, we have two kind of operation, right? One is dot operation or AND operation, another is the plus operation or the OR operation. So in logic circuit, we have two operations. One is, we can say dot operation. Dot operation means AND operation, right? Another one is plus operation, which is actually OR operation, right? For example, AB plus A bar B1. So we have dot operation or AND operation here. We have dot operation or AND operation here. We have plus operation or OR operation here. So these are the two operations. In case of dot operation, PMOS transistor will be connected in parallel. PMOS transistor will be connected in parallel. And NMOS transistor will be connected in series. Just opposite. On the plus operation or OR operation, it will be opposite. The PMOS transistor will be connected in series, and NMOS transistor will be connected in parallel.
Wait.
So don't try to remember all four, it will make you confused. Try to remember one, then other one will be just opposite. So if you just try to remember this one, PMOS will be in parallel in AND operation. In AND operation, PMOS in parallel. You can make a short form APP. AND operation, PMOS parallel. Then other will be just opposite. AND operation, NMOS series. OR operation, PMOS series. OR operation, NMOS. So just try to remember one. This is my technique. You don't need to follow me, but you can try this way. If you just try to remember all four, sometimes it will give you confusion. And just make some word that can help you to remember, memorize. APP, AND operation, PMOS, parallel. Okay, anyway, so we already get these things. We have pull-up network, we have pull-down network. In the pull-up network, we have PMOS. In the pull-down network, we have NMOS. If you have to perform the AND operation, your PMOS will be in parallel, your NMOS will be in series. If you have to perform the OR operation, your PMOS will be in series, your NMOS will be in parallel. So if you just keep these two things in mind, you can design easily any logic, Boolean expression as well as the logic circuit. So let's try. So for our information, I just put it here. So we have pull up network with PMOS. We have pull down network with NMOS, and the AND operation PMOS in parallel, or AND operation NMOS in series, or operation PMOS in series, or operation NMOS in parallel. Can you see? Is it okay? I just write down so that we can. Design a 2-input NAND gate using CMOS. Design a 2-input NAND gate using CMOS. So what is the AND gate? You have 2 inputs, A, B, and output, right? 0, 0, 0, 1, 1, 0, 1, 1. Y equals to just AB, an AND operation, right? Nothing else, just an AND operation. You have to have PMOS. PMOS will be in parallel, and MOS will be in series. As you're talking about CMOS, that means it is a complementary. We have both the PMOS and NMOS. So PMOS will be in parallel, CMOS will be, NMOS will be series. So we can draw this one. Sorry, my drawing is not that much good, but I hope you can understand. So this is A input, this is B input, we just connected in parallel. Right? We can say they are parallel. Gate to gate, source to source, gate to drain, all are connected in parallel. So as I mentioned, PMOS in parallel. Then we have to connect the NMOS. Okay. So this is NAND gate, so AB bar, right? So if you want to use an AND gate, that means you have to use another inverter here, another CMOS here. Just a simple CMOS. If you just give a simple CMOS here, it will give you an AND gate. Because here the output is Y is
AB
to
bar.
A dot B.
A dot will be bar.
So here, if you put it here, whole bar, you minus 0.
We also need to draw the inverted circuit.
No, I'm telling you, if we want to design the AND gate. Now, at first, my question is design a 2-input NAND gate.
So, yeah.
If it's a 2-input NAND gate, you can stop here.
Okay.
But to design an AND gate, you have to put another inverter. But usually, we don't need this an AND gate and NOR gate at the universal gate, right? So we actually perform by using this NAND gate and NOR gate. So that's why we just focus. So this is 2-input NAND gate. If I ask you to design a 3-input NAND gate,
3-input
3-input
NAND gate.
you just connect
Another one
another one.
in parallel.
So you just connect another one.
If it's AND gate, then we need to put an inverter.
Because CMOS itself an inverter circuit. Okay. So here, if I just want to just try with this one, so this is my B input, this is my A input, this is my VDD, right? This is my ground. So try with the truth table. So what is what? This is bit 1, 1, 1, 0, right? If I'm not wrong, the NAND operation. So when both input is 0, A and B, both input 0, this is a PMOS, both the transistor will turn on, right? This is a PMOS, bubble is there. So you apply logic 0, this 2 will be turned on, and this 2 will be turned on. So if this 2 is turned on, that means you can cut off here. You get the output, any of the path, get the output to the VDD. If you go for 0, 1 or 1, 0, if you go 0, 1, this transistor will turn on, this transistor will turn off, right? This transistor will turn on, this transistor will turn off. But when this transistor is turned off, then we have a disconnecting from here. And now the current will pass through this transistor. So it's still high. Now when both input is high, this transistor will be turned off. That means we have disconnected from here. Now these two transistors is now on. So we'll get connected to the ground. So we get right?
I have a question.
Yeah.
Why do we use 2 transistors for the current source? You could have just one.
Which
current
one?
Source, the parallel combination.
So 2 inputs, that's why 2.
Yeah, we could have just used the current source, that one transistor, and it would still work the same.
By using just one transistor, we can give 2 input.
Yeah, if you use the current source.
Or the diode connected load.
Yeah, we wouldn't need 2 transistors.
Yeah, you can use that diode connected load, for example. But the diode connected load is, you cannot give an input, then you cannot vary, right? If you just use this diode connected load.
Yes, but we only need to
So,
control
for
the
example-
2 transistors that are connected to ground. We don't need to control the transistor that is syncing the current.
But if you want to change the logic
Yes, it would still change. the
0,
logic.
how we can give you 0 here?
You don't need to put 0 there. You could just put 0 in A or B.
Here?
Try and draw 2 transistors connected to ground. It would still work.
Maybe.
Yeah,
I need to check.
Yeah, you'd only need one
So-
transistor. Yeah, instead of the parallel combination, you could just use the current source diode connected. And if you put high in A and B, you'd still get 0 because it's connected to ground.
Okay, I'll see, and we can draw. If you can draw, show me and see. And if it will work, then we can see. Okay. So we can design any AND gate, any inputs. If you just increase the number of inputs, you have to increase the number of transistor here. You have to increase the transistor here. It will give you the same result, right? Okay. Let's try yourself. 2 input NOR gate. 2 input NOR gate. Design a 2 input NOR gate. Design a 2 input NOR gate by using the CMOS. So it's an OR operation. And if you just use the CMOS, you'll get the inverter. So in the OR operation, the PMOS should be in series, and MOS will be in parallel. PMOS is in my pull-up network, and MOS is in my pull-down network. So this is OR operation. You can see here an inverter. CMOS will give you the inverter. So the OR operation, we already mentioned, for PMOS will be series and MOS in the parallel. PMOS in my pull-up network and MOS in my pull-down network. So pull-up network will be in series, pull-down network is in parallel. So if you just input 3 input, 4 input, we just keep increasing. Here also, if you just try one logic gate, one operation, if you go for 0, 1, 1, 0 and 1, so you apply 0, this will be turned on, this 1, this will be turned off. So as they are in series connection, the whole part will be cut off, right? The current will not pass through here. Now here we have 0, 1, 0, 1. So one of the transistors, this is 1, so this is 0.
Off.
So it will be off. 0, 1, right? I'm talking about 0, 1. 1, 0, sorry, 1, 0, because 0, 1, yeah, 0, 1. So it will be off, it will be on. So the output will be connected through this transistor to the ground. So we get 0, 1. So 0 will be on, 1 off, 0 off, 1 on. So here it will be, as they are connected in series, the whole part will be disconnected, and output is connected through this transistor to the ground, we'll get output signal. So part 3 will be like this. This is also 0. And if both are 0, both will be turned on, both will be turned off. If both are turned off, this will be disconnected. Output is connected through these two transistors to the DCC. Can you design the XOR gate? XOR. Design a 2-input XOR gate by using CMOS. What is an XOR gate? The logic expression. XOR equals to A bar B plus AB bar. And what is the complement of this one? We take the complement. AB. Right? This is the complement of this one. Complement of X now. Complement of X now. Why? Because as you know, we are trying to design the CMOS, output of the CMOS will be an inverter circuit. So if you try to design this X now, complement of X now, it will give you the XOR. Otherwise, if you just use this way, you have to add some another inverter circuit. So we can design like this: AB and A bar, B bar, right? AB and AB bar. So we have AND operation, we have OR operation, we have AND operation. So we have AND operation first. So this is will give you what? AB. Now we have to have designed A bar, B bar. So just an inverter will give you that A bar. We just think that we have already A bar here. So this is giving us A bar, AB. This is giving me A bar, B bar. So OR operation. So AND operation. Now for the OR operation, we will connect it in series. Right? PMOS connected in series for OR operation. We are now only designing with the PMOS, the pull up. For the AND operation, PMOS will be in parallel. For the OR operation, PMOS in series. So AND operation in parallel, AND operation in parallel, OR operation in series. So you already get these things. Now we have to design the NMOS, the pull down resistor. We still didn't design the pull down. So again, we have to design the opposite one. Now we have now this is AB in the NMOS. In NMOS, AB in parallel. In PMOS, this is a parallel. In NMOS, they are in series. Again, we have to design this AB bar, B bar. So here they are connected in series, AB. They are connected in series, A bar, B bar. The NMOS for OR operation should be in parallel. NMOS for OR operation should be in parallel. So now this line is parallel to this line. Okay? So again, so you are taking the output from here. So this will give you what? AB plus A bar, B bar, O bar. So again, I am inputting this one, this AB. So this is my original XOR. But as we are using the CMOS, CMOS will give you the complement one. So that's why we just use this one, XOR, complement of XOR. So here we can see that from the logical expression, it is nothing but AB plus A bar, B bar. So we have two product term, one OR term. So for the product term, PMOS will be in parallel. So AB, AB. A bar, B bar, A bar, B bar. You got it. For the OR operation, the PMOS will be in series. So these two connected in series. This portion and this portion connected in series. So we have done our pull-up network. Now we have to design our pull-down network. That is with the NMOS. For the OR operation, the NMOS is in series. So NMOS is in series, AB. AND operation. We have another AND operation, A bar, B bar. They should be in series, A bar, B bar. So we have two AND operations. Now for the NMOS, for the OR operation, these two NMOS should be in parallel. So this one and now this one will be in parallel. So this is the overall circuit.
I have a question.
Yes, sir.
A into B plus A bar, B bar. How did that equation become this one?
By using the de Morgan's
Okay.
theorem. Okay. What about the X naught? So X naught is also the complement, right, of A bar, B bar. Usually X naught is AB plus A bar, B bar. If you take the complement of X naught, it will be A bar B plus AB bar whole bar. Right? So that means you have to give, for example, here if you can give A bar and B, then you give A, B bar. A bar, B, A, B bar. Of course, For that complement, we have, of course, we have another inverter
Double
circuit.
complement. Now,
Okay?
so we are taking double complement to transform that.
Yeah.
Okay.
We're just using because the CMOS will give you this result. Now CMOS will give you what? Here it is A bar B, right? And this one A B bar. So A bar, B, A B bar, and whole bar. So if you take the whole bar, this is the complement of X. Okay? Easy. Just you have to keep two things in mind. Pull up resistor, pull down resistor. Pull up resistor will be PMOS, pull down resistor will be NMOS. Now we have two operations only, either AND operations or OR operations. Just try to remember one. In the AND operation, your PMOS will be in parallel. I name it APP. Just keep in mind APP. AND operation, PMOS parallel. Then rest will be just opposite. So AND operation, NMOS will be series. OR operation, PMOS will be series. OR operation, NMOS will be parallel. So you have to design pull-up. You can imagine there is a pull-up network. In the pull-up network, I have PMOS. Then in the PMOS, they will be in parallel. If they are OR operation, we need to make them series. Then we will come to here. So get design. Let's finish with one logical expression, Boolean function. If we want to implement a Boolean function by using the CMOS,
Oh,
for example, y equals to a dot b plus c plus cd. Let's try it for 2 minutes, then I'll try. Design a circuit for this Boolean algebra. A dot B plus C or C. So we have to implement one by one. At first, you have to implement all the PMOS, the pull-up network. Then you will go for the pull-down network. So in the pull-up network, we have all the PMOS, right? So we have to.
can I draw the pull down network then?
You can draw, but one by one. If you just draw the pull-down, draw your side, then come here.
Okay.
Don't go together. Complete one, either pull-down or pull-up. Okay. So if I go for the pull-up, and pull-up is a PMOS, and for PMOS, we have this option, OR operation series and operation parallel. So we can see we have an AND operation with A to the BC, and another AND operation with CD. Okay? So, and then BC is again in the OR operation. So if I draw BC, B plus C, this OR operation, that they are added with A. So that means they are in parallel, right? So this is in parallel. So A parallel with BC. So this whole portion again with OR with CD. So it is OR means series, then CD again in parallel.
But we cannot draw like with already we have given C. So what we
You
using
can
that,
bring.
how can we draw it?
It's better to draw like this, but usually we can take a shortcut here. So for example, if you want to draw again here, it will be more complex to see. So that's why we just draw like this way. So it just showing that C and D connected in parallel to perform the OR AND operation of C. Of course, this C is here, the same C. It's not a different C. So this is all about PMOS. Now you have to connect the NMOS. So I just dotted here so that I can draw here. So in NMOS, that CD will be now connected in series. This CD will be in series. See, this CD is connected with all of those things, but this B and C is OR, so they are connected in parallel, right? This is B and C connected in parallel. Now this is AND operation of A, so they will be in series. Now this part will be connected in parallel with this one. Here they connected in series, here they connected in parallel. Both part. So this is the
Shouldn't the AND operation be in series in NMOS?
sorry
The AND operation between A plus C and CD.
AND operation.
Yeah, between CD and A, B plus.
CD